I don't think this is going to change. Not all. I'm Nico, I'm from Hamilton. This is more of an exercise in philosophy of science, really, in history, rather than actual astronomy. How ideas have changed and concepts have changed since the beginning of time. So I'd like you to imagine, to start with, that you're a caveman coming out of your cave, looking at the Earth, looking at the sky and wondering what the hell it's all about. So let's have the first slide. Yeah.
You should be good to change it.
No, it's not changing. There we are. Now the Earth is flat, obviously. So how far does it go in all directions? It must have an edge somewhere. So here's a picture of the edge of the Earth, okay? What holds it up? The next one, please. Well, as we all know, the Earth is held up by 4 elephants standing on the back of a turtle, right? Now, I don't have a problem with the elephants and the turtle, but there's something else radically wrong with this picture. And that is that this is a modern concept of space. This is a modern concept of space. And the turtle and the elephants are just hanging in the middle of nowhere. It looks absolutely ridiculous. Can we have the next slide, please? Yeah, can we have the next slide? Thank you. This is a much better picture of what things were like. The Earth was flat and the sky was a dome above the Earth. How high? Nobody knows. And things moved in the dome. You know, the sun went round and the moon went round and the stars went round. So how did it all work? And what was holding the Earth up? Next one, please. Well, of course, we've got the 4 elephants and the turtle, but something has to hold the turtle up. So here's the turtle floating in a lake. But that doesn't answer the problem, because the lake has to be held up by something, you see. So there's a story I've heard about Stephen Hawking, who gave a talk, and then a little old lady stood up and said, "Oh, you're completely wrong. Everybody knows that the Earth is held up by 4 elephants and a turtle standing on the back of a turtle." And he said, "Yes, well, what holds the turtle up?" Next slide, please. She said, "Oh, it's turtles all the way down." Well, things changed. It was over 2,000 years ago that people started to think differently back in ancient Greece. Have the next slide, please. Maybe the Earth isn't flat. Maybe the Earth, the most perfect shape for the ancient Greeks was a sphere. They thought perhaps the Earth is a very, very large sphere. And of course, there is observational evidence to support that. This is one of the observational evidence that when a ship comes over the horizon, you see the masts first, and then the rest of the ship comes up afterwards. Now, of course, they didn't have telescopes to see that, but even with the naked eye, with a reasonably sized ship, you can see that. You have to be a bit careful, please. Next slide, please, because you can be misled. This is a picture taken in the UK. I'll leave you to think about what's going on there. Let's move on to the next slide. Now, I didn't take this picture, but I could have done, because this picture is taken from the summit of Monte Rosa, which is the 2nd highest mountain in Europe, looking eastwards. Let's see, yeah, there we go. No, there we are. That's the Matterhorn, that's the Dent d'Herens, that's the Dent Blanche, which I climbed a few days later. And the thing to notice is that all these mountains are lower than the one that I'm standing on. But the horizon is below the tops of these mountains. So there you can actually see the fact that the Earth isn't flat if you climb a very high mountain. The most important empirical evidence the Greeks knew, of course, is that if you change your latitude, the star patterns change and the position of the sun changes. And by measuring the position of the sun at different latitudes and measuring the angle, Eratosthenes was able to calculate the size of the Earth over 2,000 years ago. Next slide. So the Earth is a sphere. And he was right. Next slide, please. And this actually answers the question of what's holding the Earth up. The answer is nothing, because down is towards the centre of the Earth. This question no longer exists. So we've transferred the Earth from a flat sphere into a sphere, and down is towards the centre of the Earth. This is the first exercise in relativity. Not relativity of motion, but relativity of direction. All right? Next slide, please. So, what happens to the sky? Instead of being a dome, it's a hollow sphere. One thing you have to remember is that until relatively recently, about just over 200 years ago, the mechanics of the sky and the mechanics of the Earth were totally different. The laws that govern the movement of the heavenly bodies and the laws that govern how things behave on the Earth were two quite different things. So Ptolemy actually described how things move. The Earth, of course, is stationary. We're not moving, it's obvious, we're standing still. So the whole of the sky goes round every 24 hours, carrying everything round with it. But not everything goes at exactly the same speed. The moon moves relative to the fixed stars, and so does the sun. The moon goes round once a month, roughly, and the sun goes round once a year. So those obviously weren't fixed to where the fixed stars were. And then there were the planets. Sorry, can we go back a slide? So this is the Ptolemaic system, with the Earth at the centre, moon going around the Earth, and then the inner planets, then the sun, then the outer planets. Now, what's wrong with this picture? Okay, the scale is wrong, that's obvious. But there's something else radically wrong with this picture. What about the position of Mercury? We never see Mercury there. Mercury should be here. And even Venus is further out from the sun than we ever see it. So the position of Mercury and Venus is totally wrong in this diagram. So how do you explain the movement of the planets? That's not going to be so easy, because the planets don't move in a regular fashion. They loop to and fro. Well, Ptolemy, next slide please, to describe the movements of the outer planets, thought, well, they go around the Earth in a circle, but there's a circle which also they go round. So this is what's called an epicycle. And as the planet goes round the Earth, this epicycle rotates. And the planet seems to make a loop like this, which is exactly what an outer planet seems to do as observed from the Earth. So what's wrong with this picture? Ask yourself, which planet is this? Well, how many years does it take to go around the Earth? 1, 2, 3, 4, 5. There aren't any planets that go around the Earth in 5 years. Mars goes around in 2, Jupiter goes around in 12. Okay, it could be a minor planet, an asteroid, but they hadn't been discovered then. Also, epicycles didn't exactly describe the movements. Next slide, please.
Just try the remote again.
Sorry?
Just try the remote.
Okay. Oh yes, there we go. That is working now. That's great. Thanks very much. So let's just tell you a few facts about Ptolemy's epicycles. The inner planets, the centres of the epicycles, are always located on the line between the Earth and the Sun. So the movement of Venus and Mercury was due to the movement of the epicycles, not the movement of the deferent around the epicycles. For outer planets, the lines between planets and the centres of their respective epicycles are always parallel to the line between the Earth and the Sun, on the proximal side when opposite to the Sun, and on the distal side when adjacent to the Sun. And that actually describes very nicely the way outer planets seem to move. But it didn't describe their positions exactly, and many people in the ancient world did measure the positions of the planets really quite accurately. Firstly, the Babylonians, and then certain Greek astronomers measured them very accurately. So to try and explain that, they had a system what they called equants. The idea of this is that the Earth isn't actually at the centre of the deferent, it's offset slightly. So the equant of a planet is situated on the opposite side of the centre of the deferent as the centre of the Earth and at the same distance. And the centre of the epicycle moves along the deferent at a constant angular speed with respect to the equant. That did, to some extent, allow them to explain the movements of the planets. But even that wasn't perfect. Of course, nowadays, we would say that's because the planets don't go around the sun in circles, they go around in ellipses, but they didn't know that then. So don't try and reduce it to modern thinking. You've got to put yourself in their position and think, how do we explain all this? So, our friend Copernicus, he said, well, why not put the sun at the center and make the Earth go around the sun as a planet? Then you can get rid of all these epicycles. What's wrong with this diagram? Well, obviously the scale is wrong. Saturn had rings. They didn't know anything about Saturn's rings in those days. Uranus and Neptune didn't exist, hadn't been discovered. There weren't any minor planets, they hadn't been discovered. And as for galaxies and stuff, nobody knew anything about them. So this is a modern concept of the solar system, albeit scale-wise, you know, it's sort of just an illustration. But it's not the way that Copernicus thought of the solar system at all. Now you might think that's a much simpler system. Why didn't everybody accept it? Two reasons. First of all, it didn't actually explain the positions of the planets any better than the old Ptolemaic system. This is the Copernican system, the one that we're all used to. Again, the scale is wrong, that's obvious. What else is wrong with this diagram? What about the stars? They're scattered about like confetti. Useless. If the sun is at the center and the Earth goes around the sun, the stars would appear to wobble from side to side. They don't. So they must be a hell of a long way away, not just scattered around like confetti here.
Excuse me, wasn't Earth the closest planet?
Pardon?
Wasn't Earth the closest planet to the sun?
No. In Copernicus, it's as we. No, Copernicus as it is now: Mercury, Venus, Earth, Mars, Jupiter, Saturn. That was the Copernican system.
Neptune are missing. That could be what's wrong.
They hadn't been discovered. They hadn't been discovered in those days. They didn't exist. Well, they did. Well, we say they existed, but as far as the people then were concerned, they didn't know anything about them.
But you were saying what was wrong with the picture?
The fixed stars. The stars are in the wrong. They're just like confetti. They're not like that.
Based on his discovery, what was wrong?
Well, even at that time, it was obvious. Even at that time, it was obvious. If the Earth moved around the sun, the stars had to be a hell of a long way away because they didn't wobble from side to side as the Earth went around the sun. There wasn't any stellar parallax. Okay.
Could he see was Galilean moons there in that time?
He didn't have a telescope. This is before the invention of the telescope. All right.
Okay.
So unless you've got very good eyesight, you wouldn't have seen the Galilean moons. Now, the other reason why people didn't accept Copernicus for a long time was that people didn't think along those lines. In order to understand why, you have to understand a bit about classical physics. Because it was obvious that the Earth was stationary and at the center of everything. We're not moving, are we? We're standing still. So Plato, what's heaviness? Heaviness is a body's resistance to being moved from the place where it belongs. The ancient Greeks believed in inertia, but they didn't believe in inertia of motion. They believed in inertia of position, of location within the universe. Okay? And the person who described ancient physics more than anybody else, of course, was Aristotle, who followed after Plato. And he described physics very nicely as it was seen by the ancient world. So to understand a bit about classical physics, you have to understand the 5 elements: earth, water, fire, and air. And this is the way nature arranged things. Earth is at the middle, water is around the earth, air is around the water, and fire is outside the air. This is the natural arrangement of things. Also, there were 2 types of motion, and they were completely separate, completely different from one another, qualitatively different. Sorry, I'm going backwards now. There was natural motion. Natural motion is the motion of an object or substance towards its natural position. The motion is smooth and gentle. The reason stones fall is because earth is heavier than water and heavier than air. All right? The reason bubbles of air rise is because air is above water. The reason flames go up is because flames are above air. So that's called natural motion. And it's smooth and gentle. The consequences can be violent. If you jump off the top of a building, it's anything but gentle when you hit the ground, but the actual movement is smooth and gentle, right? The other type of motion is coerced or compulsory motion. This is the motion of an object or substance away from its natural position. The motion is jerky and violent, all right? Now, this included all types of animal movement. Of course, there weren't any machines in those days, apart from ones driven by animals. But it also included things like the wind and the waves of the sea. You must remember that at that time, no one had ever travelled faster than the speed of a galloping horse. And when you're on a galloping horse or on a stagecoach, it's obvious that you're moving. You're being jerked around all over the place. And the faster you go, the more you're being jerked around. The only things that travelled faster than a galloping horse were missiles, cannonballs, arrows. And obviously they were violent. Okay? Also, you must remember at that time there was no such thing as acceleration as we think of it today. It hadn't been invented. So there were two types of motion. There was slow motion, fast motion, there was smooth motion, and there was jerky motion, or violent motion. So all type of motion was either one or the other, or a combination of the two. If you throw a stone, for example, the upwards and forwards motion is coerced motion, and then its natural motion will cause it to curve down and fall to the ground. So this is how the ancients thought. So, when we come to Galileo, let's go back a bit. There is good arguments against him. And I'll just quote somebody from who argued against Copernicus, I should say. Since Copernicus does not understand physics and dialectics, it is not surprising if he is mistaken in his opinion, for Copernicus puts the indestructible sun in a place subject to destruction. And since fire naturally tends upwards, it cannot, except through constraint, remain down near the centre as its natural place. Now, to us, that sounds nonsense, but if you understand classical physics, it makes perfectly good sense. Okay? Now, Copernicus had an answer to that. It wasn't a direct answer, of course, because he'd already died. But he nonetheless thought about the argument, and he said that if the Earth does rotate, and if the Earth does go around the sun, it would be a natural motion, and therefore it would be gentle, not jerky. All right? And I can quote him if you like. What is in accordance with nature produces effects contrary to those resulting from violence. For things to which force or violence is applied must disintegrate and cannot long endure, whereas that which is brought into existence by nature is well ordered and preserved in its best state. Therefore, Ptolemy has no cause to fear that the earth and everything will be disrupted by a rotation created through nature's handiwork, which is quite different from what art or human intelligence can contrive. Ptolemy had wondered if the earth rotated, but it was inconceivable to him. If the earth was rotating, we'd all be being shaken around and the wind would be rushing through our hair and everything. Okay? Yeah, this is Ptolemy. The motion would have to be exceedingly violent and its speed unsurpassable to carry the entire circumference of the Earth around in 24 hours. But things which undergo an abrupt rotation seem entirely unsuited to gather body to themselves and seem more likely to fly apart. The Earth would long ago have burst asunder and dropped out of the skies. That was Ptolemy's concept of it, long time before Copernicus. But anyway, Copernicus said, yeah, it's natural motion, so it's gentle, so we don't necessarily feel it. But even then, people weren't convinced. A simple body cannot have two natural motions opposed to each other, for we see the Earth moving naturally to the centre on account of its natural heaviness, But if it is said to rotate, its circular motion will be coerced, not natural. Therefore, it's false that the Earth rotates with a natural motion. Thus, Copernicus' hypothesis is completely overthrown. That's all based on good classical physics. So in overthrowing Copernicus, you don't just have to overthrow the Ptolemaic system. You have to also overthrow classical physics. You have to accept a new type of physics. So that took a little while for people to get their heads around. And the person who really probably made the most contributions to start with was Galileo, who made lots of contributions. He made a lot of contributions to terrestrial mechanics. He rolled objects down slopes and timed very carefully how long it took for them to roll down. So he was one of the first people to toy with the idea of acceleration as we nowadays think of it. He also understood that motion in a straight line could be something you don't feel, and he quoted, imagine a hold of a ship in a harbour, and this inside the hold of the ship, things are moving around, there are animals flying around, you're walking around, you're dropping things from the ceiling. Then you imagine the same ship sailing across the sea at a constant speed. If you were inside the hold, you wouldn't be able to tell that you were actually moving at a constant speed. Everything would still be happening in the normal way. So Galileo actually had the first idea that motion in a straight line, if provided your surroundings were also moving, you wouldn't be able to distinguish it. So hence the concept of inertial frames of reference. So that was quite a significant contribution to terrestrial mechanics. And he has sorted out the mathematics of that, which is fairly simple mathematics. You just add a distance onto everything over a period of time and it all evens out at the end. It's not terribly difficult. It's called Galilean transformations. He was also, as far as astronomy is concerned, he didn't actually contribute to the mechanics of astronomy, but he did, of course, provide a lot of observational evidence through a telescope. The moons of Jupiter, of course, very important. We all know about that. But also the phases of Mercury, or of Venus, I should say, the phases of Venus he observed. There was no way that you could explain this using epicycles and equants. And on the Ptolemaic system, there wasn't any way that you could explain that, whereas you could explain it very nicely on the Copernican system. Eventually, of course, the Copernican system was accepted, and there were two important empirical discoveries that confirmed that. This chap is called, James Bradley, who was the third Astronomer Royal. He succeeded Edmund Halley, and he discovered relativistic aberration of light. When you look at the position of the stars, they shift slightly due to the speed of the Earth in its orbit around the Sun. He was actually trying to measure stellar parallax, but he didn't succeed in doing that. But he did discover that the position of stars does actually shift very slightly, rather like the wind appears to shift when you're on a boat and you change direction. It's the same thing, and he was able to calculate the speed of light in astronomical units per hour anyway, and he was able to calculate the time it takes for light to travel from the Sun to the Earth. So that was the first independent confirmation that the Earth does move, and that does it go around the Sun. Rotation of the Earth, of course, is different, and this, of course, is Foucault's pendulum, which demonstrated very nicely the fact that the Earth rotates. But this was a lot later, of course. Now we're going to talk a bit about observation and theory. Some people were good at one, some were good at the other, some were good at both. On the left we have Tycho Brahe, who was, of course, the greatest pre-telescopic observer, who logged the positions of the planets and the stars very, very accurately indeed. He had an assistant. Well, he started in Denmark, in Ven, an island off in the Baltic. but he was eventually thrown out from there and he moved to Kiel in Germany. And he had an assistant called Longomontanus, fantastic name, Longomontanus, I love that. He collated a lot of Tycho's observations, but he didn't actually provide any original work. Succeeding him was this chap on the right, Johannes Kepler, who was a great theoretician but a lousy observer. He made a complete cock-up of the observation, trying to observe the transit of Mercury. But he was a very great theoretician, of course, and he thought, well, the positions don't really add up very well with the systems we knew. He was particularly concerned about the orbit of Mars, which didn't fit into what was known at the time. And he thought, well, perhaps the planets don't go around the sun in circles, perhaps they go around in ellipses. And of course, he developed Kepler's three laws of motion, of planetary motion, which we're all familiar with. That the planets go around the sun in ellipses. They sweep out equal areas over equal time. And for different planets, let's get this wrong, the square of the period is proportional to the cube of the major axis or semi-major axis. And a series of tables were made. He made a series of tables called the Rudolphine tables. There were lots of tables made of star positions and planetary positions going right back to Babylonian times. There was the Almagest, of course, in the 8th and 9th centuries by Ptolemy. There was a Spanish sets of tables of Toledo, the Alphonsine tables in the 15th century, or in the 15th century, Regiomontanus, and Landsberger tables. And then he produced the Rudolphine tables. So we're now going to move to Lancashire in the UK. And this is a young man called Jeremiah Horrocks, who was a brilliant guy. He was both a brilliant observer and a brilliant theoretician. And he lived in the 17th century. He had telescopes, very simple refracting telescopes, but he also had access to measuring instruments. His family were clockmakers and they made him quadrants, and he was able to measure the positions of stars very accurately. He made a lot of original contributions. First of all, he observed the positions of the planets very accurately. He found that the Rudolphine tables were very, very accurate. These are the ones that Kepler produced, whereas the previous tables, based on Ptolemy's system, weren't. So he was convinced that Kepler was right and that Copernicus was right. His most famous contribution was he both predicted and observed, the first transit of Venus. And this is a picture of him observing the transit of Venus. He also worked out that the moon orbits the Earth in an ellipse by observing it very accurately. And he, as far as the Rudolphine tables were concerned, they were absolutely spot on, apart from Jupiter and Saturn. Jupiter was gaining very, very slightly, about 1 minute of arc every 10 years. Saturn was losing slightly. And he looked at the positions over the previous couple of centuries or so, and he found that Jupiter tends to jump ahead when it passes Saturn, and Saturn tends to fall back as Jupiter passes it on the inside. So it's almost as if the two are attracting each other. Now, he didn't have an explanation for that, but it was an interesting observation. And as I say, he observed that the moon orbits in an ellipse. He hypothesized the mechanics in terms of rotation and magnetism, but this was before Newton, so he didn't actually come up with a mechanism, but he was thinking along those lines. Very bright guy. He died at the age of 22. Relatively suddenly. We don't know why he died, but he was due to meet a friend called Crabtree, who also observed the transit of Venus. And the two of them were due to meet up, but he never turned up because he died. So nobody knows quite why he died. This was just before the English Civil War, and a lot of his writings were lost during the English Civil War. So he was a very bright guy indeed. Sorry. Anyway, anyone know who this is? This is René Descartes, who's a French guy. He was a mathematician and a philosopher. I think, therefore I am. You remember that? Cogito ergo sum. That was him.
Isn't he the guy who made the robots?
Made what?
Didn't he make those characters that would move in France with water?
I don't know about that. I'm not sure. What he did do was he developed coordinate geometry, which of course was a predecessor to calculus, really. And he really predicted Newton's first law of motion, that a body not acted upon by unbalanced forces travels in a straight line at a constant speed. Then, of course, we come to Newton, who wasn't an observer as far as astronomy was concerned. He relied on the Astronomer Royal, Flamsteed, for the observations. But he was, of course, probably the greatest theoretician, certainly the greatest theoretician before Einstein. And his contributions, of course, were huge. Sorry. You've got the telescope, reflecting telescope that he invented, work on light, and of course, most of all, his mechanics, laws of mechanics, Newton's laws of motion. Now, you know these. I'm not going to stress all this. You must remember that the Principia was published in Latin. That was the lingua franca in those days. And even for the academics, reading it was actually very difficult and very abstruse. Nowadays, we understand it quite easily. We can put the words into English. The actual words he used in Latin for momentum was quantity of motion, which is mass times speed, quantity of motion. Nowadays, we talk about momentum. And of course, then the mathematics of mass, force, and acceleration all were tied together for the first time. Also, there's your rockets for you. Also, of course, his law of gravity, and he developed calculus. And you have to have calculus in order to demonstrate the truth of this equation and the equations of motion. And using calculus, he was able to derive Kepler's laws from his own equations. And that's how he really tied things together. So for the first time, terrestrial mechanics and celestial mechanics became linked. So the laws that govern the movement of the planets and the star and well, not the stars, they were too far away, but the movements of the planets and the moon and the sun were the same laws as governed the movements of objects on Earth for the first time in history. Newton also spent a lot of time doing alchemy, which nowadays we think of as some sort of voodoo, sort of superstitious nonsense. But of course, you must remember that alchemy was the father of chemistry. And what he was actually trying to do was to understand chemistry. Now, he didn't make any great advances in chemistry. That was left to others later, people like Lavoisier and Mendeleev and Humphrey Davy, John Dalton, the people who made the advances in chemistry. Newton didn't. Yeah, I'm going to talk a little bit about the orbit of the moon. Horrocks, of course, demonstrated that the moon's orbit is an ellipse, but a lot of time was spent in the 17th and 18th century working out the orbit of the moon. Why was that so important? Well, tides, yes. I mean, that's a fairly simplistic, that's fairly obvious and fairly, once with Newton's laws, you can work that out fairly easy. It was important for two reasons. Firstly, to predict eclipses, But most importantly, it was for navigation, determination of longitude. Determination of latitude was fairly straightforward by observing the height of the sun and the stars above the horizon, but you couldn't determine longitude, and sailors at sea could not determine their longitude properly. And they were trying to use the moon as a sort of astronomical clock, because it moves relatively quickly through the heavens, 1 lunar diameter per hour. And by plotting the position of the moon very accurately, the idea was that you could work out the time at Greenwich. And if you know your local time, by observing the position of the sun, you can work out your longitude. Okay? So people like Bradley and Maskelyne spent a lot of time plotting the orbit of the moon. It's elliptical, eccentricity that. The axis of the ellipse precesses at about 40 degrees per year, 8.9 years per complete cycle. The orbital planes incline 5.15 degrees to the ecliptic. The moon is one of the few satellites that doesn't orbit in the rotational plane of the planet. Jupiter, Saturn, Uranus, and Neptune, the satellites all orbit quite close. Well, a lot of the satellites, not all of them, but a lot of the main satellites orbit in the same plane as the rotation of the planet. Look at Uranus, it's tipped right over on its side. Its moons go round, in the same plane. Not so our moon. Our moon is much closer to the ecliptic. But the plane retrogresses at about 20 degrees per year. So that's a very complicated thing. Of course, Newton tried to work this out using his law of gravity. But it's actually impossible to do that. 2 objects, you can work things out very precisely using Newton's law of gravity and Newton's laws of motion. 3 objects, very, very difficult. And even nowadays, you need massive computers to work out how even 3 objects are going to move if they're all attracting each other and affecting each other. So with the orbit of the moon, you've got the Earth, the moon, and the sun. One question I was going to ask you, is the gravity of the sun on the moon or the Earth on the moon greater? Is the moon falling towards the Earth faster than it's moving towards the sun, or the other way around?
Towards the sun.
Pardon?
There's a greater pull from the sun.
Yeah, there's a greater pull from the sun, which is a little bit counterintuitive. You think, well, it's going around the Earth, surely it's closer to the Earth, so the attraction to the Earth should be stronger. But it's not actually. The sun's about 400 times further away than the moon. 400 squared is 160,000, so the sun would have to be 160,000 times as heavy as the Earth to give the same pull. The sun's actually more than twice as heavy as that, 333,000 times as heavy as the Earth. So actually the moon's falling towards the sun faster than it's falling towards the Earth. Now we don't notice that because the Earth's also falling towards the sun at the same speed, so we don't notice it. But that's an interesting thought. Yeah, so for navigation, that was the reason it was so important. But of course, the person who actually solved the navigation problem wasn't an astronomer at all. It was John Harrison who made the first accurate chronometers that worked at sea over long periods of time, so that time could actually be measured accurately on a rolling ship over a long period of time. And he was the guy who actually solved the longitude problem. Since then, of course, things have changed. We've got radio telecommunications, so it's really not a problem anymore. Okay. Yeah, just to finish off, we've got a few other things to add in. This, of course, is William Herschel, who was a great observer and who discovered the planet Uranus, by luck more than anything. But he was a very good telescope maker. He was actually a musician by profession, but he was the best telescope maker in his day. He must have been a very skilled guy because he was using speculum metal to make his mirrors, which is extremely difficult to work with nowadays. And this is a replica of the sort of telescope, it's about a 6-inch, I think, could be a bit bigger, that he discovered Uranus with. One thing I should say about theoreticians, some people are very good theoreticians and not very good experimentalists. There's a great story about Wolfgang Pauli, who was a nuclear physicist, who was one of the greatest theoretical physicists of the last century. He was one of the main people who developed quantum mechanics. and nuclear physics. But whenever he came near the laboratory, all the experiments would go wrong. He had some sort of electromagnetic aura about him that completely screwed up all the experiments, and they tried to keep him out of the laboratory as much as possible. Yeah, he couldn't do the experiments at all. Okay, now of course Uranus didn't move as expected. It speeded up and slowed down, and they thought, well, that's a bit odd. It didn't sort of keep to its orbit as worked out by Newton's laws. So these guys actually put their heads, well, they didn't put their heads together, they were working independently. This is Urbain Le Verrier, who's a Frenchman, and on the left, and on the right is John Couch Adams, who is British. They both independently worked out that this could be due to another planet further out, and they predicted the position of the planet. John Couch Adams went to the Astronomer Royal, who was called Airy, but he didn't take much notice of him. Le Verrier went to a number of people, but he eventually went to a chap called Johann Galle at the Berlin Observatory, who discovered Neptune, less than a degree away from where Le Verrier predicted it would be. And this is the telescope that discovered Neptune in a museum in Berlin. It's a 9.5-inch refractor. So that was the first planet to be discovered by theory before, so that was a very important discovery. So up till then, everything was perfect. Everything worked very nicely. We got the mechanics right. We knew exactly how everything worked. Certain assumptions were made about discovering Neptune, most notably a thing called Bode's law. Have you heard of Bode's law? It's not really a law. What it states more or less is that each planet is about twice as far away as the previous planet. In fact, it's slightly less than twice as far away. And it does work roughly. Neptune is actually slightly inside Bode's law. Of course, there's a gap between Mars and Jupiter. But of course, planets have been discovered in there. The minor planets have been discovered in that gap to fill it up series. And everything was absolutely perfect, with one tiny exception. And that was the orbit of Mercury. Mercury orbits around the Sun in an elliptical orbit. And the axis of that orbit precesses around the Sun very slowly. It's interesting that observing Mercury is actually very difficult. So how did they work that out? The answer is, of course, transits of Mercury. During a transit of Mercury, you can work out its position and time it extremely accurately and get the position very precisely. The axis of Mercury's orbit precesses around the Sun at slightly over 300 arc seconds per century. It's an incredibly small amount. I'm amazed they could actually work this out so precisely. Le Verrier calculated how fast it should precess using Newton's laws and the gravitational effect of all the other planets. But it was precessing around too fast. The exact amount wasn't known, but by the end of the 19th century, they'd worked it out by observing very carefully that Mercury was precessing around the Sun 43 arc seconds per century too fast. So what was the explanation for this? Well, the most obvious explanation is that there's an undiscovered planet. This is what Le Verrier himself thought. He actually predicted a planet orbiting inside Mercury. He called it Vulcan. Never turned up. Vulcan was never discovered. What other explanations? Well, perhaps Venus is more massive than people had supposed. The mass of Venus we can't work out very easily because Venus doesn't have a satellite. But you can work out the mass of Venus by the effect on the Earth's orbit and the effect on the Earth's orbit in relation to the Sun and in relation to transits of Venus. In order to explain the perihelion of Mercury, it would have to be 10% more massive than had been worked out, and that didn't fit in with other observations. So what's the only other explanation? Well, perhaps the only other explanation is that Newton's law of gravity isn't quite right. Now that was unthinkable to us Brits. But there was, of course, a man who realized that Newton's law, if his theory was right, wouldn't be quite right. And that, of course, was Albert Einstein, general relativity. And in powerful gravitational fields, Newton's law isn't quite right. So he set out to calculate, using general relativity, what the orbit of Mercury would do around the Sun. And he worked out, he couldn't do the full calculation, of course, he couldn't take into account the effect of all the other planets, it would have been far too complicated. But what he could do is to take the Sun and Mercury as a two-object system and work out what would happen. And he discovered that Mercury would precess around the Sun at 43 arcseconds per century. In other words, he explained the discrepancy between theory and observation very nicely. So that really brings us to the end of our journey through the solar system, from the flat Earth and the dome across the sky, through the Ptolemaics, through the spherical Earth, the Ptolemaic system, Copernican system, Newton's laws of motion, and ultimately general relativity, to a full understanding of how the solar system works. So I'm just going to finish off with a few other things. Anybody heard of this chap? He's a French mathematician, very famous mathematician. He was one of the first people who understood relativity, at least special relativity anyway. He was also a philosopher, and he was interested in science. He said, science does observations. You observe facts. Which facts do you observe? There's an infinite number of facts. You cannot just arbitrarily observe facts and get science. It would be like a monkey trying to type the Lord's Prayer with a typewriter. You know, you have to select which facts you observe. Which facts do you select? Well, the answer is ones which are generally true rather than specifically true. Generalized facts are much more useful. And you can then do observations to confirm that. After a while, it becomes boring. So what becomes boring then, what becomes interesting then, is exceptions to those rules. You can make generalized rules based on general observations. It's the exceptions that are interesting. And you look for the exceptions, either the very large or the very small. Cells are more interesting to biologists than whole animals to some extent. Stars and the universe and galaxies are more interested to astronomers than small things. And then you produce hypotheses to try and explain what's going on. Where do the hypotheses come from? They don't come from nature. Nature doesn't give you hypotheses. All nature gives you is experimental data. Hypotheses comes from within your mind. How do you recognize a hypothesis? He never explained this. But thinking of hypotheses is actually the easiest part of science. And you can never test all the hypotheses. So which ones do you test? The easiest and the most elegant ones, he said. Test them and then move on from there. Right, we're just going to finish up with a few quotations. How are we doing for time? Yep. Okay, pretty good. Not bad. Okay, we're just going to finish off with a few quotations. Max Planck, you've all heard of Max Planck. Who hasn't heard of Max Planck? He started the quantum theory. He was a reluctant revolutionary who discovered the equations that predicted that energy was not continuous, that it came in little packets. German scientist. Science cannot solve the ultimate mystery of nature, and that's because in last analysis, we ourselves are part of the mystery we're trying to solve. New scientific truth does not triumph by convincing its opponents and making them see the light, but rather that its opponents eventually die and a new generation grows up that's familiar with it. René Descartes. If you would be a real seeker after truth, it is necessary that at least once in your life you doubt, as far as possible, all things. Now, he doubted everything, of course. And the fact that he realized that he doubted meant that he realized that he thought, and therefore he existed. That was his basis of his philosophy. If one regards himself as a skeptic, it's a good plan to have occasional doubts about one's skepticism. That's quite a good one. I quite like that. There are two ways to be fooled. One is to believe what isn't true. The other is to refuse to believe what is true. There are two ways to live your life. One is that nothing is a miracle. The other is as everything is. The end. That's it.
observation.
Yeah.
As useless as the Ptolemaic system is today, it still has at least had one mechanical use, at least until from the mid-20th century until now, and that is in this mechanical design and implementation of the planetarium projector.
Yes.
That's
Yes.
its only remaining use.
That's right. Yeah.
I think go to the planetarium, which I went to in Nagoya at the end of last year. It's got one of the last purely mechanical projectors. There you can see gear trains in motion that are putting the planets onto the sky, and they look entirely by that Ptolemaic system.
That's right. Yes, projectors in planetariums use epicycles effectively to make the position of the stars move. Yes, that's absolutely right. And the Ptolemaic system was just as accurate as the Copernican system in terms of describing how they move. Yeah.
To the point that Copernicus even had to throw in epicycles as well. So Kepler to remove them with ellipses.
Yeah.
And we can't make elliptical.
No, it's difficult to make elliptical.
We can do them now.
Projectors.
Well, we can do them now, but practically speaking, I think the precision necessary for a good planetary projector. That's still the case even today. Not quite good enough. It has to be Ptolemaic for nothing.
Yeah, that's absolutely right. So for projecting the orbit of Mars, it might be quite tricky.
I've got some gear train diagrams from the early Zeissers. It's literally, as you'd expect, a combination of two planetary gears appropriately, and then a pair of offset gears with a single pinion bar between them to allow for the movement not only backwards and forwards but also up and down, with a pair with the planetaries at an angle to each other to match that motion.
Oh, wow. Very complicated, yeah.
So would Copernicus have been more accurate if he had made every one two across the planets, twice as far as the last?
Wouldn't have made any difference, I don't think.
But would you have considered his diagram more accurate?
He wasn't very accurate anyway. He didn't know how big the solar system was. Nobody did in those days. Horrocks was actually the first person to realize how big the solar system was. Up until then, they thought the astronomical unit was about 8 million kilometers, 8 million miles. Horrocks, when he observed the transit of Venus, saw that the shadow of Venus was a lot smaller than he'd imagined. Looking at Venus through an early telescope, there's a lot of glare around it, very difficult to measure the size through one of those early telescopes. But with the shadow projected on the screen during the transit, he was able to see how big Venus was. Now, he assumed that Venus was similar size to the Earth, slightly smaller than the Earth. And then he was able to calculate the astronomical unit, and he estimated it at 60 million miles. Okay, it's only 2/3 the true figure, but compared to the 8 million miles that most people thought of in those days, he was the first person to realize, to sort of be in the right order of magnitude as to how big the solar system was.
This may be a dumb question, I'm not a physicist, but you mentioned the great difficulty of calculating how three bodies will respond to each other gravitationally. But then later you said that people were able to make fine predictions about exactly how Mercury would move in response to the gravity of all the other planets and the Sun together.
Yeah. Leverrier, he was looking at a constant effect, really, rather than trying to describe individual exact motions, I think. He was looking at a more constant effect. I don't know, I'm not a mathematician. I'm not a mathematician, so I can't actually explain the mathematics. But, but you can sort of add together the effects of the planets, allowing for their distances, that they have a sort of overall effect using Newton's laws. And as I say, I don't understand math, but you can do that to work it out. It's slightly different from trying to predict the exact position of something at a particular time, especially with the moon, with everything changing like that. He was just looking at the precession of the axis. That's the only thing he was looking at. He wasn't looking at exactly where the planet would be at any particular time. I can't really sort of answer that any more precisely than that. Yeah.
I was just, that's one little quote you had at the end, I pulled up one of Shakespeare's. There's some of Shakespeare where he's sort of debating about Aristotelian philosophy and Copernicus, and there's the one in Hamlet that goes, doubt thou the stars are fire, doubt that the sun doth move, doubt truth to be a liar, but never doubt I love you. And then I think it was Hamlet to Ophelia.
Yes.
But it's actually throwing in some astronomical debate into that.
Yeah,
those two
absolutely.
lines.
Yeah.
You mentioned that the moon is falling towards the sun. Could you elaborate a little more on that?
Well, obviously, I say falling towards, it's not getting nearer to the sun. It's accelerating towards the sun, but because it's in orbit, it doesn't get any closer to the sun. But it's actually accelerating towards the sun twice as fast as it's accelerating towards the Earth. But we don't notice it because the Earth is accelerating towards the sun at the same rate. So we don't notice it. That's all I'm saying. Because intuitively you think, well, obviously the effect on the moon must be greater than the effect of the sun, because the sun's a lot further away, but actually it's not.
Look out, the moon's orbit around the sun. The curvature is always towards the sun.
Yeah, exactly. The curvature is always towards the sun.
All the Earth tells us flat curvature.
Yeah, that's right. Exactly right. Yeah.
Do you know who invented the word gravity?
Gosh, no, I don't. Can you tell us? It must come from ancient. It comes from an ancient language. Gravitas means weight. Gravitas, in Latin means weight or. Sorry.
It comes from the Greek language.
Yeah. And gravitas is a very ancient word. We use the term gravity now, knowing what we're talking about, but ideas were much more mixed up in those days.
Cool, thanks very much.
Okay,